Now, in this lecture, we'll be discussing phase-space trajectory, phase-space trajectory, and the concepts involved in plotting phase-space diagrams, and all you need to know about phase-space diagrams. Now, phase-space diagram is quite interesting. If you understand the concept very well, then it will be easy for you. Please listen carefully. Now, for plotting phase-space diagram, you must follow two rules strictly. You must follow what? Two rules must be followed strictly. Two rules must be followed strictly. Now, which are they? Now, they are if motion of the particle. Now, I'll write down the rules. If motion of the particle is in plus positive z direction, or you can say that it's in the x direction or y direction. I'm just taking z here. I'm just writing z only. You if motion of the particle is in the plus z direction, you can say uh, if it is in z direction, the momentum is taken to be positive. Momentum will be positive, and just the opposite. If motion of the particle is in the negative z direction, the momentum will be negative. Now, this is just a sign convention. If you remember how we took the sign convention in the case for lenses and mirrors back in plus two and all, we'll definitely understand. This is just a sign convention, just like that. Now, I can't afford to change this sign convention. Now, the sign convention is just to write it just again simply. Sign convention is just take plus z means what? Momentum is positive, and minus z means momentum is taken to be negative. Okay, now in order to understand how to plot phase-space diagrams, we need the help of various problems, and one such classical problem is of the ball bouncing on the ground, and we'll get into the problems. Yeah. I think this. I'll take this one as the first example where the ball is bouncing off the ground. Now this is the ball. Now this ball is at a height h. This ball is at a height h, and we can see that this is z equal to 0, since this is the ground. This is z equal to 0. This is the ground, and yeah, we can see that at this position, at the top position, the velocity will be 0. Since at the highest position, velocity will be 0, and this is at a height h, and z equal to 0. This is z equal to 0, since this is the ground. So we'll be plotting the phase space trajectory of a ball bouncing, and now I'll draw the phase space diagram. I'll show you how to draw the phase space diagram. Now we take the position in the horizontal direction, which is z, in the horizontal direction, and the momentum p in the vertical axis. Yeah. Yeah. Okay. Now, let's see. We can see that the ball is bouncing, and now this is a mechanical process. The only force that is involved in this process is gravitational force. The only process involved in this is gravitational force, and gravitational force, as we all know, is a conservative force. So the mechanical energy remains constant. So now what is the energy? That's what I'll be discussing now. Now, what is the energy? E is equal to the total energy. E is equal to half mv square plus the potential energy mgz. Now, at the highest position, what will be the total energy? At the highest position, I told you that at the highest position, the velocity will be 0, and the total energy is mgz. Now, kinetic energy and potential energy can interchange, but the total energy remains constant. This they can interchange, but the total energy will always remain constant. Kinetic energy and potential energy can interchange, but the total energy always remains constant. Now I'll be showing how to draw the phase space diagram. Now, initially the ball is at a height h and it is coming down. uh, it's coming down from this position at a height h. Now when it's coming down, now this is the first step. This is the first one. This is coming down. Now when it's coming down, it's moving in the negative z direction. As told you, when it's moving in the negative z direction, the momentum should be negative. Before that, now where do I plot this particle in this diagram? Now it's at a height h. That means it should be at the z axis at a height h, right? At a height h. Now the particle is here at a height h, and now the particle is coming down. So if the particle is coming down, what will be the phase space trajectory? Just see, this will be the phase space trajectory with the direction this, because you need the momentum to be negative. That's why I've drawn like this. Now I think it's easy to understand that the momentum will be negative. And what will be the momentum here? Now at z is equal to 0, now this is the position when the ball has reached the ground. Now at z equal to 0, what's happening? At z is equal to 0, energy is equal to the kinetic energy. So instead of half mv square, I'll write it in terms of momentum. That is p square by 2m, where p is equal to plus or minus root 2 me. So what would be the momentum at this position when the ball has reached the ground? I told you that it will be negative if it's coming down, and so the momentum will be minus root 2 me. Now, yep, that's that of the ball coming down. And in the next step, we take, now this ball has reached here. Now this ball has reached here, and the second step, in the second step, now the same ball is going up. Now the same ball is going to go up, and I assume that it reaches its initial height again. I assume it to be an elastic collision where there is no loss of anything. It will it will reach back to its initial position. Now when it's going up, now you can see that it is going up again. When it's going up, in which direction is this moving? Now it's moving in the positive direction, and when it's going up, this momentum minus root 2 me current shift so quickly to plus root 2 me. So it shifts to plus root 2 me, because the velocity, I mean the momentum, now it's going in the positive direction. So this has to be in the momentum has to be positive. But you can see that as you can see, when it's going up, you can clearly understand that the velocity is decreasing, and so momentum will also decrease. Now what will be the phase space diagram here? I mean phase space trajectory. It will go like this and reach here. Now why did this trajectory go and reach in the z again? I told you that this is, I assume this to be elastic, where the particle or the ball goes back to its initial state, and there is nothing, if it had lost its energy, or if it weren't elastic, it would not have reached that position. I mean the z position here, it would not have reached here. So this is just a basic example. I hope you understand uh, what's involved here, and I hope you understood what are the concepts. And yeah, this direction is very important. This direction shows you the actual meaning or actual concept, because without this direction, if you mark this direction wrong, then it is absolutely wrong. And I hope you understand the phase space diagram. This is just the phase space diagram of a ball bouncing uh, off the ground. Yeah, just an easy topic. Yeah, this is just it. and we'll discuss more problems in the next lecture. We will be discussing phase space trajectory and we'll be doing some more problems in the next lecture.